So this is joint work with primarily Scott Garabrandt, who is here. Scott, can you indicate? All right. So this man over here is like the primary source of the ideas in this paper. Then the four of us have sort of like crowded around Scott as a sort of carbon rod arrangement to like absorb the neutrons of like logical induction that have been coming out of him into a controlled reaction that like people can eventually understand. So you can, I guess I'll eventually have these slides or some slides very similar to them probably on my website. So if you want to look at them, you can Google Critch. They might, I don't know if they might end up on intelligence.org or not, but that's that. I'll just wait a little bit. Looks like there's like a, yeah, fire hazard. We don't want to kill all the people who understand logical induction. Huh? Yeah, let's do lights. Yeah. All right, so rough plan for how this talk is going to go is first I'm going to say what logical induction is. Seems important. Then I'm going to say a little bit about why we care about it, because first it's intrinsically super cool. Like you don't almost need to care about anything to care about logical induction. But it also we came to it from caring about long-term concerns about the control of highly advanced machine learning systems or artificial intelligence, and so we'll talk a little bit about that. Then I will, I guess, probably I should be over here in order to be able to point with my left hand, since this thing doesn't work. So then we'll get into like the technical stuff, and then I'll like try to save a little bit of time at the end for interpretation. Like, what does this all mean? Who are we in the universe? Okay, so here is a little table that I'd like to use to illustrate what we mean by logical induction. So suppose I've got a 10-sided die like this, and I roll it, and I ask you, what's the probability? I roll it, I cover it up, and I ask you, what is the probability that that die landed 7? So that's probability d10 equals 7. And if you think about it for a minute, you'll say 10%, right? Oh yeah, can you guys nod if things I say make sense and like make weird squinty faces? Yeah, okay, cool. Make weird squinty faces if it doesn't make sense. All right. So if you think about it for a minute, you'll say 10%, and if you think about it for a day, you'll still say 10%. If I've still covered, if the die is still covered, you will still think 10%. And no matter how long you think about it, you'll think 10%. At the opposite end of this spectrum, you can have a question like, hey, what do you think is the chances that the 10th digit of root 10 is 7? So if you think about it for a minute, you'll probably say 10% because you don't know, right? But if I let you think long enough, and maybe if you've got some paper, you might be able to figure out that it's probably not 7. Like you'll do some calculations and you'll be like, man, I don't think it's 7. But like maybe I screwed up, but I really don't think it's 7. And then if you think for infinity, which I apologize, sorry for leaving you in the room with the paper, but you will eventually converge on an answer of 0 because it is not 7. And then there's something in between, which is what we see going on in machine learning all the time, which is where you've got some observation, like maybe right before the die was covered by the cup, you got to see like, you got to see it for a brief moment while it was like tumbling. Does this make sense from this picture? I don't know if you can see a little bit of blur there, right? So you see it, and at first you don't have time to think about it. You're like, yeah, 10%, right? But if you think about it longer, you can like run some simulations. If you're a human or if you're an AI, you might run a bunch of simulations and realize, actually, based on what I saw going in, it looks like a little more likely to be 7 because 7 was looked like it might come up. Does that make sense? So you have to think about it to change from this 10% to this 15%. And if you thought way, way longer, maybe you could get it even more precise, but eventually it would like top out, like you maybe still don't have enough information about like the shape of the table under the cup or something. So you still can never be quite sure how it ended up. So this is like a mixture. This is one kind of uncertainty. You could call it empirical uncertainty. And it refers to uncertainty you have because someone didn't tell you some information or you didn't observe something in the world. This is a different kind of uncertainty. It's uncertainty not because someone didn't show you something, but because you haven't had time to think yet. You're not waiting to do an experiment or see anything in the world to know the digits of root 10. You just need to think about them. And then this is something in between. You see something and you have to think about what you saw. Okay? So, probability theory, if you go on Wikipedia and look up probability theory, you'll see some axioms that tell you how these probabilities right here should relate. Once you've fully integrated all the information that is presented by your observations, there are certain coherence laws that probabilities have to satisfy. Like probability of A and B should be less than probability of A, right? Things like that. Or probability of A and B plus probability of A or B has to equal probability of A plus probability of B. Have you guys seen stuff like that? Right, so there's some rules that probabilities have to satisfy, but it takes a little bit of time to satisfy those rules. You have to think. You have to think about stuff to like figure out what your probabilities are going to be. And while you're thinking, you know, you might not satisfy all the rules. You need like some time to like get your shit together and have coherent thoughts. Logical uncertainty and logical induction is more about the horizontal movements in this table. So I'm going to refer to, so there's two interesting questions you could ask that are not answered by probability theory. One is that like what are like good ways for probabilities to change over time? Like what's the definition? Probability theory sort of tells you like the definition of like good coherent beliefs once you've thought about stuff. But what's the definition of like a good way to change your beliefs over time as you think?
Accumulation of predictable information.
So the interesting thing here is you're not accumulating any information. You've already accumulated the information right here when you've seen the snapshot, and now you're just thinking. So that's a really important distinction. Like the step from here to here would be accumulating information, or rather from here to here, right? Whereas in the information theoretic sense, information refers to an unobserved random variable, and here you've already observed as much of the thing as you're going to observe, and there's this other thing you have to do. Like so, you see the snapshot, and then you have to think to like process the information. Yep.
But then, did you misspeak when you said for snapshot 2, maybe you ran some simulations?
Well, it depends on how you think, right? So maybe you think in simulations, maybe you think with some other heuristic, maybe you just write down some differential equation and just say, I don't know how you do it. Maybe you just feel, when you're humans, like just kind of feeling something out, like how does it look like it was going to fall? It's kind of like a simulation in your head. Yep.
Oh, sorry,
yeah.
Do you have a way of drawing that dividing line between, say, the computing that gets you to having seen the blurry 7, like the the photons to your mental representation, versus the line of now I have the information and I'm thinking about it? Yeah,
you can draw the line, but the interesting thing is in our theory that we'll get into later, you'll see that you don't have to draw the line. You think that's fair to say? You can mix in, because when we start mixing in axioms with observations or something, we're not going to really talk much about it, but I think the answer is that you don't have to draw the line. So there's one question is like, what are good ways of probabilities changing over time when you're not making new observations, you're just thinking about stuff you've already seen? Okay, so what rules should these things satisfy? There aren't many rules in the literature or papers about like what's a good way of doing that. And another question is, obviously there's something intuitive about 50% being like a bad answer here, right? If I'm asking you to guess probability of a digit, you're going to probably use 10% until you've had some time to think about it, right? So is there some theoretical framework that we can define that would imply this intuitive judgment of ours that like, 50% would be like a dumb answer to start out with here, and like 10% would be a good answer to start with, right? And then you're still going to have to think to get to 0 or 100 eventually. Because this is completely determined by your observations. The answer is completely determined by things you've already seen. Okay, so does that make sense? Logical induction stuff is about like, hey, what's a good place to start? And like, what's a good way to evolve your beliefs over time? When you're not getting new information, you're just processing what you've already seen. Cool? Yeah.
Is it for the 50% thing, isn't that just like equal outcomes, number of outcomes?
Yeah, so you could say, if there's an equal number of outcomes, maybe they should all have equal likelihood, but should they? I mean, why not just have 7 is 50% likely to be true, and the other 9 are each, 50 over 9% likely to be true. Like, you need to make some argument, and you'd like to formalize that argument. We'd like that argument to be like written down in math, so we can do proofs about it. Cool. So that's what we're going to be talking about, and I like to say that. Oh, well, we'll get to that. So the question is now, why do we care about this thing? That's the question is, how do we do the purple stuff? And why do we care? Well, the reason I care, and I would, different people at Mary might have different nuanced descriptions of like why they care, but we want to reason about highly capable AI systems before they exist. We want to develop theories of safety and control and alignment for very, very powerful thinking machines that could do a lot of good for us if we like name them in the right direction. And it'd be great to have those like aiming theories before the super powerful thinking machines are like around. So we'd like to have theories of AI, very, very strong AI systems before they exist, or rather like how to use them and how to direct them. So we want to, how can we, it's this hard problem, right? You often hear people say like, we can't really work on AI alignment because we don't have AI yet. We don't have highly advanced machine learning systems. We don't have, and if you're in Jessica's talk, I'm sure she maybe convinced you that there are things we can talk about now. But if you weren't, I'll convince you that there's even other things that you can talk about now. Because we can model AI, whatever it is, it's going to be good at stuff. We could just develop a theory of things that are good at stuff, okay? And then try to like decide how we're going to aim the thing that's good at stuff for various values of stuff. So what do we think, what do we already have theoretical models of good at stuff for? Well, choosing actions, there's this rational choice theory. I don't know if you've heard of the von Neumann, raise your hand if you've heard of the von Neumann-Morgenstern theorem. Awesome, right? So you've got this theorem, some of the Spark, yes, Spark students know about it. So there's these theorems that tell you, if your choices between gambles or your choices between random outcomes satisfy some very modest conditions that seem very unobjectionable, then there's a function whose value you're maximizing the expectation of. So there's this like nice theorem that helps you think about what is an agent or a system that's really good at choosing between actions. Well, if it's really good at choosing between them in a way that's like not self-contradictory, it's going to follow this V&M theorem. And modulo some adjustments to the V&M theorem that you might want to make. But part of the V&M framework is this belief thing that the agent has, right? So we had this rational choice theory, and you've got, if you look at the axioms of V&M, there's these probabilities that it believes. Okay, so now we need, really to cash this out, we need a theory of like how probabilities and beliefs might behave, and we have that, it's called probability theory, and there's nice theorems like Bayes' theorem that tell you how, when you get new information, how your beliefs should adjust after you think about that information. So this is sort of what you're thinking of earlier when you're saying, yeah, accruing the new stuff. But similar to how rational choice theory depends on probability theory to formulate it, to be formulated or to be realistic, probability theory depends on this thinking step, this step where you got the information and now you have to like figure out what your new probabilities are. And so implicitly in probability theory, there's this like missing component, which is, how do you figure out what your probability, what do you think before you're done thinking? What are your beliefs before you've finished figuring out what they are? And there wasn't really a theory for this. There's been like various fragmented attempts at like making such a theory. But we'd like to say an AI is going to be good at rational choices, it's going to be good at probability theory, and it's also going to be good at whatever the heck this purple stuff is. So we'd like to say we'd like to define good at purple stuff so that we have a model of AI before it exists. And there's all kinds of other features of AIs that we'd like to have models for, and this is just one such feature, good at purple stuff, good at logical induction. And so the way that we're going to use these words, logical uncertainty is like the state that you're in before you've finished figuring out the logical consequences of your belief, of your observations. So you are logically uncertain about the digits of square root 10. You know the definition of square root 10, so you know everything you need to know in order to logically infer the digits of root 10, but you're logically uncertain because you haven't finished doing the logic that you need to do to figure it out. Does that make sense? So logical uncertainty is the state that you're in, and then logical induction is how you deal with that state. It's how you refine your beliefs over time. Cool. So any questions about like what this means and like why we care about it? Before I go on to stuff. Yep.
What if it's not that good at stuff? Would you not be concerned with it, but it's like better enough?
You mean like a future AI system that's like not that good at logical induction? Yeah, so there's different ways it depends on like the nature of the not good at it. So if you can say a particular failure, like a particular bias that we'll have, then you can say, okay, it's going to make these types of errors. But even to define a bias, you need to say what good judgment is, and then a bias by definition is like deviation from good judgment. So we can't even, like before we define good judgment, we can't even begin to start to talk about your question. Yep.
Why hasn't this been developed already?
Scott Garibrand was too young. I don't know. That's my answer. To be honest, I thought about this a lot in high school. I had lots of mathematician friends. It makes sense, like when you're seeing some talk about the Goldbach conjecture, you know, and someone says like, oh, we discovered like this new class of numbers that are all expressible as sums of primes, right? Your belief in Goldbach conjecture goes up, right? But like, how much should it go up? Right? You've observed no new empirical information. You knew what primes were. You knew the definition of addition. So logically, Goldbach, unless it's independent, is just a logical consequence of stuff that you know. Nonetheless, you go around adjusting your beliefs about it in response to other like, you can think of the mathematical community itself as like an algorithm that's like proving stuff and discovering stuff, and it's like updating its like intuitive beliefs about stuff. And mathematicians, a lot of my friends in math at some point have this crisis of like, what are we doing? Like, what are the principles we're following when we have these like fuzzy beliefs about which theorems are true or false before we even prove them? So then you go through this crisis of like trying to define what are the good principles for like having your beliefs about conjectures, and then you give up because you're not Scott Garibrand. So this happens, and anyway, one day Scott Garibrand doesn't give up, and we have logical inductors. So you could try to define what does it mean to be good at the purple stuff, good at the at refining your beliefs while you think about them. And a lot of people have thought about this before. There's various criteria in the literature that sort of gesture at like, well, here's one property that we expect good logical uncertain reasoners to have. We want them to be computable. We want them to be we want them to eventually satisfy probability laws after they think for a while. So if A implies B, eventually we want the thing to have probability of A less than probability of B. So there's all these other properties. I'm not really going to get into them because we'll see them in a lot of them in finer detail later in the talk. But I just want to sort of point at, you know, since really at least as far back as the 40s, you've had people talking about criteria for good logically uncertain reasoning, and but they're sort of informal, kind of like you're saying, like, oh, like, you know, equal, like bunch of outcomes should all be equally likely until you've had reason to think otherwise. But you have to figure out first of all that the outcomes are mutually exclusive in order to even apply that. So there's some thinking you need to do first. And so part of the progress that we've made is we've adopted a formalism where we can state versions of a lot of these properties and then check if they're possible or not. Or we can prove that they are, or prove that sometimes they're mutually incompatible. So that's already a step forward, is just the framework of talking about a common language. We're talking about all these sort of like informal approaches or different formal approaches to logical uncertainty in the past. And I think there's lots of interesting questions about applications, like how we're going to use this. And I'm going to defer those until after we've concretely seen the math, because it'll be much easier to like point at the object once we've seen some math. I guess I've already had. Are there any more questions about just like what the logical uncertainty thing is? I think we've had a bunch already, so it seems good. Okay, so I believe now my slideshow is going to tell me to switch to Beamer, where I can do math. Whoa, that's the wrong. Here we go. This is a talk I gave at Spark. This is the logical induction one. Okay. So the way the technical part of the talk is going to go is I'm going to formally state the definitions of logical induction and some desirable properties of it. We're going to talk a lot about the properties. We have an algorithm and a criterion that implies a bunch of nice properties, and the algorithm satisfies the criterion, so that's nice. And I'll talk about those. and then I'll talk about formalizing the criterion, which is actually requires more definitions than talking about a lot of its properties. We'll talk about the algorithm a little bit, maybe time permitting, and then I'll switch back to PowerPoint and talk about like some conclusions. So let's get to the formalizing. We're going to choose a language or a formal system of logic, gamma, for encoding statements about variables and computer programs. So who's heard of piano arithmetic in this room? Awesome. Okay, so that was like about 70%. So piano arithmetic is a language. We're talking about arithmetic, but it turns out that you can encode lots of statements about computer programs in piano arithmetic and then prove stuff about them. So it's a very expressive language. We want our language to be pretty expressive because obviously we want AIs to be able to like think about computers. I think, or we want our theory of AIs to include AIs that think about computers. And then this capital lambda is going to be the set of all sentences expressible in gamma. And then a belief state, we're going to define a belief state. That's the state that you're in while you're still thinking about stuff. Is a map from sentences to probabilities that is constant outside a finite set. And I think we've toyed with different definitions where it's constant outside the finite subset or 0 outside the finite subset. It sort of doesn't matter. The point is, if you're kind of writing down your beliefs, you're only going to be able to have written out like a finite number of beliefs at any finite time. So think of your belief state as just like a list of probabilities that you've managed to assign to stuff so far. And we don't want to say, at this point in talking about the theory, that your belief state is like whatever you implicitly believe, or your like revealed beliefs or your revealed preferences. They're like things that you've managed to explicitly write down. Because if you define your beliefs to be something that's derived from your preferences or derived from your actions or derived from stuff that's already in your mind, then you're no longer separating the belief and the computation. And the whole point of this framework here is to separate the belief and the figuring out of the belief. So your belief state is just the stuff that you've written down probabilities for. And a reasoning process is just like a sequence of belief states. So at each time step, you like adjust your probabilities to all the sentences that you've seen so far, and maybe you add some more sentences that you have beliefs about. Does that make sense? Cool. Any questions about that? Sweet. So now with this definition, we can say what is a good reasoning process. So some properties you'd like to have for a good reasoning process is that it should be computable, or at least our model of it should be computable. We would like it to converge. We'd like this thing not to be like flip-flopping around forever, changing its mind about stuff. Like we'd like it to be eventually figuring out what it thinks about a thing. So that's convergence. And that means to say that we've got this symbol p sub n of phi. So that means like the probability that you assign at time n to sentence phi, or phi, should I say? I think I'll say phi. And we want, as n approaches infinity, for that limit to exist, and we're going to denote it by p infinity. So it's what you will eventually converge to thinking after forever. You'd like the limit to be a probability distribution. So once you're done computing your belief update at the end of time, you'd like to satisfy the laws of probability, finally. So that's these kinds of rules. And there's this other property that people have talked about that I think is desirable, which is that if you never disprove something, you shouldn't think it's impossible. So if you don't prove it, you shouldn't think it's 100%. So that's what this says. If your logical system doesn't prove something, then you're not going to be 100% sure of it. Does that make sense? So these are some nice properties, and in fact, we knew before Gare-Brandt induction that these properties could be satisfied. A guy named Abram Dembski had an algorithm that satisfied these. And the paper that is sitting in draft form on that table right there shows that those properties are related. So there's a single property that I'm going to call the Gare-Brandt induction criterion, which implies all four of them. So that's kind of nice. It means that like intuitively we were just, as humans, just kind of generating these desirable properties, right? And you might think that the only thing they have in common is that humans want algorithms to have them. But they have another thing in common, which is that they follow from the Gare-Brandt induction criterion. And that sort of validates us as intuitive generators of criteria, that we managed to generate a sort of coherent set of criteria to be satisfied. Us as in humans, like all the people who've been working on this field. It also shows that the properties are feasible because we have an algorithm that I'm going to call Logical Induction Algorithm 2016, or LIA. And I'm putting the 2016 in there because, like, you never know, people are going to update these things. People might pick this up after we're done with it and make it better, and I don't want to steal the name logical induction algorithm forever. Someone else might make it better. So we know that those things are feasible, and also they're extensible. There's a bunch of other awesome properties that follow from the Garrett induction criterion and are therefore satisfied by the algorithm that we have. So that is the deal. That's like what's going on here. We got an algorithm that does the purple stuff good. Okay. So here are some properties that the algorithm satisfies. It's actually faster to state the properties of the algorithm than it itself, or even the criterion. But we'll get to the criterion. I just want to it's kind of like before I start giving you this like big fat definition of an algorithm or a criterion. It's nice to like care, right? So let me tell you what properties it has. I don't think you should care what the definition of the algorithm is or the criterion before you know what properties it satisfies, because otherwise you'd be like, whatever. So there's this non-dogmatism property, which is that it's like a stronger version of the dogmatism property from earlier, which is that if you have any algorithm that outputs sentences, and it outputs this like infinite list of sentences that are consistent, so no pair of them are contradictory or contradictory with the theory gamma, then there's actually some constant such that all the sentences in that sequence are above probability epsilon. So it's stronger than the earlier property. And here's another strengthening of the earlier property, which everyone loves, Kolmogorov complexity. You can actually say for a given sentence, if it's never disproven, then its probability is going to be at least some constant times 2 to the minus its complexity. So there's a nice relationship between how complicated the thing is and how likely it is. And that's why we call it the Occam bounds, because Occam is the Occam's razor. You should, if something's real complicated, you shouldn't believe it. Well, that's not quite right, because of a real complicated disjunction, you should totally believe that, right? real long disjunction is probably true. So you need to amend it a little bit. There's some relationship between complexity and believability, and like this is probably the good relationship that you want. And again, these are all talking about the limit, right? These are all talking about the probability distribution that our algorithm will converge to. We're not yet talking about what it thinks along the way. Yeah, question?
Sorry, is that sharp? Do you know?
Is it sharp? No.
Like, well, there's a.
You don't have an example that
I mean.
So there's a C here. Yeah, I'm sorry, yeah. So I guess you could take the supremum over all C such that this is true, and then it would be sharp.
Like the C we can prove it for is probably like
not sharp.
Than, like,
Yeah.
C.
Right. Yep. Yeah. Any other questions about these properties? Actually. Cool. Where did I? I gotta rearrange something because this phone over here should totally be in my left pocket, where my left hand goes. All right. So there's some nice properties. Now here's where it gets exciting, because people have been wanting like math to understand math for ages. Like Hilbert was like, hey, can we like put math on a mathematical foundation? And Gödel comes along and is like, no. And then Pudlak comes along and says, sort of. I don't know if you're familiar. So there's some results that say that logic can sort of believe that it's like sort of trustworthy up to a certain bound. But I think that, well, yeah, these are real cool. So our logical inductor, as we'll call it, or our Gauss-Brandt inductor, is going to believe, it's going to come to believe in the consistency of the logical system that it's using. So if we define con n is there is no proof of contradiction using n or fewer symbols in our logical system, then eventually at time step n, our Gauss-Brandt inductor believes any algorithm satisfying the Gauss-Brandt induction criterion is gonna believe in the consistency of gamma up to that point. And in fact, there's a stronger claim, which is I'm going to call belief in future consistency. You can actually choose any computable function. So it could be n to the 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 n, whatever, some crazy function. Eventually, on time step n, our reasoner is going to believe that gamma is consistent up to proofs of length f of n. So this is like an extremely strong belief in consistency, that you can basically pick your favorite computable function, and our algorithm is going to believe in consistency up to that function. So it's very, very strong. And you can view this as self-reflection or reflection on the deductive process that it's using. But here's a more explicit self-reflective property. This is basically, it knows what it knows. So at time step n, for large n, at time step n, a Garrabrant inductor knows what its own beliefs are. So roughly speaking, if you have some sequence of sentences that are, I'm going to call this polytime generable. In fact, I've got a definition. We're going to elaborate on this in a later slide. But it's like you have an algorithm that takes in n and spits out a sentence in time polynomial in n. So you've got this polytime generable sequence of sentences, and at time step n, our inductor is going to, if its beliefs are like kind of squarely between A and B, like A and B, between A and B by like this epsilon margin, does that make sense? It's like forgivingly inside the AB interval. Then it's going to know that its beliefs are actually inside the AB interval with very, very high probability. It's going to be like almost complete. So it's kind of like saying, if it's between 89 and 91% sure of the Riemann hypothesis, then it's going to be 99.99% sure that it is between 89 and 91% sure of the Riemann hypothesis. It can be quite certain of what it thinks. Yep.
Sorry, asking a question, but when you say no, is that like has a representation of in the algorithm?
Yeah. No, it has written down.
Okay.
On time step n, it has written down, this is my probability already.
So that includes like the regressive form of I know A, I know that I know A,
Yeah.
I know that I know that I know.
Yeah. Yeah.
How do you deal with that?
So at any finite time step, it's only going to have regression up to a certain n. Yep. But like, yeah, at time step large n, it's going to know that it knows some finite number of no's. Yeah. Yeah. Great question. And so now, when you get self-reflection like this, you've got something that believes in its own consistency. You got something that knows what it knows. This is like ripe, fertile soil for like paradoxes, right? We can, so we should all be getting nervous. But in fact, this thing has like a very strong systemic immunity to the liar's paradox. You can find a sentence that basically it's equivalent to saying, our Garrabrant inductor doesn't believe me. Okay? You can write down a sentence that says, pick your favorite rational probability P. You can write down a sentence that is equivalent to saying, I am less than P likely to be true. So P could be like 1%. I am less than 1% likely to be true. And the Garrabrant inductor just handles the situation. It's just like, no problem. I know what I'm going to do. It assigns it probability P in the limit. And on the way to the limit, it does this crazy thing where it like is constantly flip-flopping its belief right around probability P so that it's less than P of the time. Yeah? So good. Yeah. So good. All right, I'll just say that again. So you make a statement that says, I am less than P likely to be true. I'm going to say P% because it fits natural language better. Okay, so I am less than P% likely to be true. And then over time, its beliefs about that statement converge to probability P. But they like over time, they like oscillate just around P so that they're actually less than P% of the time. And they're actually, so it works out. Yeah. So you don't get a paradox, and it's awesome. I just cannot. Yeah, in fact, people are already like seeing what happens when like agents that try to make themselves unpredictable by like trying to, like you can make an agent from a Garrabrant inductor that tries to make itself unpredictable by first trying to predict its own actions and then having a plan that if it can predict its own actions, it will do the opposite. And by virtue of that counterfactual plan, it can't be predictable. And then you get random behavior. Okay, anyway, it's real cool. So Liar's paradox resistance is real cool. And moreover, you can go so far as to say that this thing kind of trusts itself. So this is another, these are properties like that Miri has been sort of pining for like years, just like how can we have a model of an agent that like trusts itself, trusts its future self, understands itself, knows what it knows, etc. And this algorithm just like does it all. So it trusts its future self in the following sense. We have a result that is roughly interpretable in quotes. Those are human quotes, not Gödel quotes. These are the Gödel quotes. And those are the human quotes. So we have a result that roughly says that the that should be a sub n there, apologies. But the probability at time step n that you assign to a statement phi sub n. Again, sorry, I'm assuming that we've got this sequence of polytime generable sentences. And I'm going to harp on the meaning of those, I think coming up soon, yeah. And the next slide is going to like harp on how important that polytime general thing is. We got some sequence of questions we're asking the inductor that's polynomial time generatable or generable. And roughly speaking, it has some property like this, that the probability that it assigns to phi, given that its future self, so f of n is some large number, given that its future self assigns probability at least p, is at least p, asymptotically. So this is like saying, if future me thinks that we're 90% likely to live on Mars, then I'm 90% likely to think we're going to live on Mars, because future me is smart. He's had more time to think. So conditional on future me believing X, I believe X. Yep.
Given that you don't know what future me is going to believe, what explanatory power, why?
Right, so why is this, so this property is good because you want this thing to be able to reason about hypothetical actions it might take. Like, right? Like if someone says, Critch, don't go to Berkeley because the cognitive science department is going to like suck you in and you'll never do math again. I'm like, well, if future me thinks cognitive science is a good field of study, it's a good field of study, so I'm just going to go to Berkeley and not worry about it. Does that make sense? Like I have this confidence that if future me thinks it's a good idea, don't worry, right? So if future me thinks something is true, yeah, it's probably true.
Knowing what future me thinks by current.
So this is conditioning on what future me thinks. It's different from knowing. It's like, suppose future me thinks it's at least probability p, then it's probably at least p. This is a conditional probability.
And the thing that updates the condition, like to get to the future state, that's the definition of the inductor?
Nope. The cool thing is the inductor is an algorithm. Step 1, it's an algorithm. Step 2, algorithms can be written down formally mathematically. Step 3, this algorithm has beliefs about every mathematical statement, including statements about itself. So you can just write down this statement. That's what the Gödel quotes mean. It means like mathematically represent the statement future me assigns at least probability Pn, and then ask it, conditional on that, what do you think the probability is? And it's like, well, at least that. Now, this is in quotes because it's not quite true. For example, there are denominators, like things could go to 0. It's a bit tricky. So the actual result looks like this. And there's a bunch of definitions that I would have to say to make that true. But you can like just stare at it a little bit, get a sense of the shape of it. You laugh, but I mean, this is how, I don't know, when I read a paper, the first thing I do is figure out the shape of, the results in it. So it's something like there's some indicator function for whether this thing is true, and you multiply the binary variable that indicates whether this thing is true by that thing. And then you take an expected value, which I haven't defined at all, but there's expected values of logically uncertain variables, which is cool. So anyway, there's some kind of future trust thing going on here, which is really great because we really wanted agents that can like reason about their future, and like these hypotheticals where it thinks its future, like it's not gonna try not to go to Berkeley because it's afraid of getting sucked into cognitive science. It's gonna be like, well, future me thinks that's a good idea. It is. Questions about that, actually? This is like, maybe it's kind of deep. Maybe we should have I see lots of like faces doing that. So maybe I should just let you guys do some logical induction right now before I present you more.
Yeah, maybe some of the confusing could be just like whether you're actually endorsing this as an actual thing for humans to
Oh. No, I'm right. I see. Yeah. So I'm not telling you to like buy lots of addictive substances and put them in your house and trust that future you will make good judgments about them. Thank you. Yes. Yes?
Like super crude, just pattern matching. That looks sort of like Cauchy-Schwarz, but the other way around. Is there...
There is there are like there are these like sequences of like bounds on stuff that are really what's going on. Yeah, for some values of what you meant, you could be right. Yeah.
Like you can think of that as like Bayes' theorem, where the denominator has been multiplied. Well, not Bayes' theorem, but like the definition of conditional probability.
Yeah, and you like multiplied this thing over.
Okay.
Yeah, but again, I just wanted to let you stare at it. If you want to know more, you have to go to the paper. It's right there. Okay, so that one probably I don't know quite yet. I was at a math camp with these guys, so I don't really know what's in the abridged version yet, because it got cut down while I was like away. But you notice I keep bringing up these like polynomial time general questions, right? So hopefully you care now when I give you this definition, because you've been like irritated with it for a while already. The interesting thing about sentences that are generable in polynomial time is that they're easy to generate relative to like other more complicated complexity classes, but they can be arbitrarily hard to answer. So there are polynomial time algorithms that can write down questions or statements of uncertain truth value that are just like, I want to say uncomputable hard to verify, but what I really mean is harder to verify than any computable function of the sentence number.
So like
say again?
like humans?
I don't know if humans were generated in polynomial time, actually.
That sentence might in fact be an example.
Well, I don't know if you use polynomial time to generate it.
An example would be like busy beaver of n is greater than 1, busy beaver of n is greater than 2.
Well, here's one. Here's an example in the next slide. So if you let g of n be the statement, there is no proof of g of n in fewer than f of n characters. Pick your favorite giant function f, okay? And then make a sentence that says, this sentence cannot be proved in under f of n characters for each n. Now, you might wonder, how can you make a sentence that refers to itself? That's a trick called Cantor's diagonal lemma. And actually, there's a version of it that lets you have this parameter n in it. So just trust me, you can look up in Boulos. There's ways of like actually writing down sentences that are provably equivalent to these self-referential predicates. And you can see if gamma is consistent, it's not going to be able to prove this in fewer than f of n characters. All right, suppose that I've got a sentence that says, I'm not provable in less than 1,000 characters.
No, I get it.
Okay.
The implication is then you have something that basically says this cannot be proven.
Well, it just says you can't prove me in under 1,000 characters. You can prove it in 1,001 characters all day if you want.
Oh, okay.
Yeah.
But then you still haven't proven it. You can't prove it. It can't be proven.
After 1,001 characters, you've proven that thing is true. This thing is true. There's a proof of it.
Yeah,
But it needs to be very long. Think about it. Do logical induction. All right. So this statement is true, right? If gamma is consistent, this statement can't have a proof, a short proof, and that's what it says. It says I can't have a short proof, so that makes it true. So, and in fact, because the proofs, you can actually write down an algorithm that will search for a proof of this. That algorithm will provably terminate. So there is a proof of this thing, and it's at the very least, at the very most, as long as like an exhaustive search of all strings up to whatever length you need to prove it. Which is not f of n, could be much bigger than f of n. But this thing has a proof. It's true, but its proof is crazily badly long. Does that make sense? But it's very easy to write down. You write this down in log n time. You can actually write down a template for this sentence and just like keep substituting in longer binary strings for n, right? And then this thing just gets crazily hard to verify. And you can roughly see that. So nonetheless, we have this amazing property called provability induction. And provability induction says that if you can generate questions, if you can generate statements in polynomial time that are provable, it doesn't matter how awfully long their proofs get. A Garrabrant inductor is going to catch up to your sentence generator and start believing the sentences as soon as you generate them. This warrants pause. Okay, I'm going to like draw a like kind of cartoon depiction of this thing because I think it's this is a problem. This is a property that we were not looking for that we just got. It just showed up and we were like, whoa, really? or at least I was just like, what? So we've got our sentences, phi sub 1, phi sub 2, phi sub whatever, and they're all provable, but we're just like crazily badly long proofs. So at time step 1, imagine our Garrabrant inductor looks at sentence number 1. So imagine the Garrabrant inductor's running along over here, and like Ramanujan is like running along over here generating his super hard to verify conjectures. Okay? And Ramanujan spits out phi sub 1, and Garrabrant inductor's like, man, I don't fucking know. 50%. I don't know if that's true. So then at time step 2, it still has a belief about phi 1, and it's like, I don't know. It's hard. I don't get this thing. And then it also has been asked another question, which is phi sub 2, and it's like, yeah, I don't know that either. Okay, just let me think, please. Okay, so these sentences are like coming on. There's this like onslaught of conjectures, phi sub n, right? These mathematical conjectures that are presumably being generated by some here like intuitive algorithm that uses heuristics to generate true things, or maybe some like concoction like I just made that's guaranteed to be hard. And eventually one day, you know, at time step like, you know, 10,000, it's like, whoa, hang on, guys. That was true. I figured it out. All right, so it's like 100%, or like something very close to 100. And then you're like, all right, so it's finally caught on to the first thing. It believes the first thing, and then you're like, what about the second thing? And it's like, I don't know. That's still, I'm thinking about it. Okay, so it's still like roughly 50%. And then like much later, maybe at like p a million, it starts to believe both the first and second sentences. 10 to the 6 I should have there. Does that make sense? By time step a million, it has managed to verify like the first 2 sentences, and it's still super uncertain about these ones. So this looks doomy, right? It's like, it looks like the number of sentences it has to consider, right, is like is like getting linearly wide, but like the difficulty of verifying them is like super narrow, right? So it looks at this tiny little cone of things it's going to believe, but no. One day this just stops and it catches up, so that like time step super large n, I don't know, maybe it's a Google, I don't know how big a number you need. It's going to depend on the particular algorithm, but it's actually going to catch up and just believe, it's going to widen out, and it's going to believe even statement number n, as soon as statement number n gets generated.
I'm sorry, what assumption were you making about the generating process of the speeding?
It's polynomial time in n. So at each time step n, there's an algorithm that spits out a new sentence, and its runtime is polynomial in n.
Assuming that it's filling in a template.
I mean, it's assuming they're similar in some way.
Yeah, they're following some kind of pattern, exactly. So it learns that pattern. Yep.
So just to clarify, these are like provable statements that you're feeding, like.
Right, you've got some algorithm for spitting out statements that happen to be provable. They're not quite they don't have to be quite a template in the predicate sense. Like they don't have to be a first order predicate with an n in it, and you keep plugging in different n's. The nature of the sentence could look very different, but they do have to have something in common, which is that there's a single polynomial time algorithm that's generating them, and the point is that it catches on to that pattern. If there's a pattern that it can catch on to, then it does. Yep.
Does it automatically assign the last one 100%?
Like very close to 100%.
Okay, but not actually 100%.
Yeah, for every epsilon, there exists a large n.
It's not like eventually always.
Yeah, well, this is the statement right here, right? So for every epsilon, there exists a large n, such that on time step n, it assigns probability very near 1 with an epsilon. Yep.
So does your inductor like know that it's being that like? Wait, so it doesn't.
No, it doesn't know that someone's out there with an algorithm. It might. Induction. Yeah, it figures it performs induction. Yeah. Yeah. Unfortunately, mathematical induction was a term already taken to refer to deduction. So we had to call it something else. Yep.
Think a little bit later about how information enters the system, but like, let's say that's
in this system right here that we're examining, there's no information entering it. Yeah. This is all in between, like, I've received some data, I've written down some facts about the data, and now I'm like thinking about the consequences of those facts. No new information. Yeah. That's the whole point of this framework. Yep. You could make modifications where you like throw in extra information while it's thinking, and that'd be like future papers, but like we're well prepared to like have versions that do that. Yeah.
So does all of this apply only when the poly time generated sequence Are all true statements or provable?
When they're all provable. Now, great question. So what happens if like half of them are provable, right? Yeah, so it does a great job then too. So let me get to that. So we're going to have lots of limits. So we made this notation. This sequence is like roughly the same as this sequence, means that their limit difference is 0. This is a common notation for asymptotic. This one's like roughly bigger than that one if asymptotically the limit of the other one minus the first one is, or second one is 0 or more. So the situation where the inductor catches up to the pattern that's generating the questions, we're going to call that assigning its beliefs in a timely manner. Like this is the timely belief, you know, at the time that you might ask it the question, the belief it assigns at that time is its timely belief. It's the one that it managed to generate on time when the question is made. Who's the next person in this room, by the way?
I'm not sure. You have about 8 minutes. I can look up people.
Cool. Thanks. So there's this cool another cool property, which probably this will be the last cool property that we'll be able to say in detail, but it says if you have a polytime generable sequence of statements, then if the logical inductor is going to converge to some pattern of probabilities that it assigns to those statements that is also polytime generable, then actually you don't have to wait till infinity. It's going to start assigning those probabilities in a timely manner. So anything that is any polytime pattern that it's going to believe at time infinity, it's actually going to believe along this diagonal here eventually. So you can prove lots of cool stuff by first proving it using p infinity and then saying, and now there's a large n where it works. So now I have to.
4 minutes, there's a 40-minute break.
Cool.
And if you want to take more questions, you can go to the Poly West room.
Great. So what I'll do is I'll conclude in such a way that people feel comfortable leaving the room for a break, and then I can stick around during break and answer more questions. So.
Take people to the Poly room.
Oh yeah, we can't have break in here?
No, because
Got
they come and set up the next thing.
Got it. Makes sense.
You just migrate.
Makes sense. I'll just bring my laptop. All right. You know, there's this question of like what happens if half the sentences being generated are true. We have theorems that say, you know, that it at least does well. So it might actually figure out which ones are true. So it doesn't have to say 50%. It just says these ones are true and these ones are false. But if it can't do that, then it says 50%. And we need to define what it means to can't be able to do that. But if it can't figure out the pattern and it falls back to using probabilities, it learns to be coherent. We had a theorem that says that it's coherent at time infinity, meaning it satisfies the laws of probability theory. But actually, you can write down what it means to satisfy a law of probability theory and show that it approximately satisfies laws of probability in a timely manner, like on this diagonal for large n. So there's a bunch of nice properties. They're in the paper. They're going to be more and more papers. And so the formalization of the algorithm is basically finance. You just make a stock market of traders that are betting on the sentences, then you imagine that market, and then whatever the market believes, you believe that. So the algorithm is actually very simple, and the criterion is very simple to state, which is part of what makes it so beautiful. It basically, the Garrabrant induction criterion, the single criterion that implies all those myriad lovely properties, basically there's some definition of trader, which warms my heart because I used to be a trader. And it says that you are good at logical induction if any trader who's not willing to plausibly risk losing more than a bounded amount is not going to be able to make infinite money from you. So if you walk up to a Garrabrant inductor and you promise yourself you're never going to risk losing more, like going negative $1 million in debt, if you promise yourself that, you're not going to make $1 million betting against it. That's just the definition. And from that one definition, you get all those amazing properties. So pretty cool, I think. And we have the algorithm. I think it's a financial solution to the computer science problem of metamathematics. And time permitting, I will use a whiteboard to answer stuff. So probably I'll take the whiteboard out to wherever it is that I would be able to field questions. And what does all this mean? So switch from Beamer to PowerPoint. So my summary of what I think just happened at MIRI is that we had rational choice theory. We had a concept of an agent in it called von Neumann-Morgenstern agent. We had some nice axioms that implied that type of agent. we had nice arguments for why those axioms are important. If you don't satisfy them, you lose a bunch of bets, right? And then we have like various formalized versions of V&M agents, some where the utility functions are reinforcement, some that aren't. Then we have probability theory. Again, we have a notion of an agent, some axioms that you need to satisfy, some like arguments that say those are good axioms, right? If you don't satisfy them, you lose money. And then we have like a formal thing called Solomon induction that just does Bayesian updating, and you know it's possible to do computably because there's this thing. So now we have another row to the table. We've got logical uncertainty theory, which can be used to like implement probability theory, which can be used to implement rational choice theory. We've got an agent concept called a Garrabrant inductor. We've got arguments that say Garrabrant inductors are like good reasoners. We know that they can exist because we have this algorithm that does it. And we don't actually have this yet. We don't have, so it's like open field of fertile inquiry for lots of math people to try and figure out like what would be the analog of these axioms that would like imply like some nice modest conditions that seem like, oh yeah, you could totally satisfy those. And then it turns out if you totally satisfy those, then you happen to satisfy like the big strong Garrabrant inductor criterion. So from here, like I said, you can have people working on improving those axioms, like coming up with like a short list of modest looking axioms that imply the Garrabrant induction criterion. You could use the Garrabrant inductor as a model for thinking about future AI systems. For example, it turns out in principle that AIs can actually outpace deduction in this absurd way. They're like absurd. They're faster. You can have an algorithm. In fact, Leah 2016 has the property of being faster than deduction by a margin that is any computable function. Like pick your favorite computable function. The algorithm is faster. Like induction outpaces deduction by that margin for every computable function. So it's kind of, I don't know if that's good or bad, but it means that like as much as there might have been lots of complexity arguments for like how you're never really going to be able to make AI. Maybe someone recently made a blog post about how those arguments don't make any sense. I roughly agree with that. But this is like a clear illustration of like actually you don't need deduction. You can use induction, and it's like computably faster for every value of computably. So that's kind of cool, and it like helps us think about what's an AI capable of in principle. And of course, then there's other approaches to AI alignment that won't necessarily use Garrabrant induction as a model explicitly for how AIs are going to work in the future, but they are going to have to eventually implicitly or otherwise address the problem of like, well, AIs are going to have beliefs before they finish thinking. They're going to make decisions before they finish thinking, so the beliefs will be implicit or revealed in those decisions. And Miri is going to focus on this stuff. I think this is sort of a consensus that we maybe don't need these axioms as badly as we need this theory of like how to make AI safe and well-directed in the future. So we're going to work on that mostly. Hopefully our models of game theory, which are currently super weak and like ill-prepared to refer to AIs for lots of reasons, like they don't have open source agents. We're going to be able to think of game theory situations where there's like an agent interacting with the world and replace the previous logically omniscient agents with like more realistic sounding bounded, logically uncertain inductor agents that are more realistic. Still not that realistic, but like way more realistic than the stuff game theory and economics and mechanism design has been talking about to date. And we've learned that inexploitability is easier than I thought. I wasn't expecting it to just be like, you can imagine there's all these properties you want to satisfy and all these people who are trying to exploit you. And it turns out you can use Brouwer's fixed point theorem to make an economy where all those people trying to exploit you cancel each other out. And that's the proof. So somehow, inexploitability, you can like balance, you've got this like pressure from all these people trying to exploit you, and you can like overcome, you can just like, all the pressures can like balance out. I don't think we knew that until we had this result. Self-trust is possible in ways that we didn't think maybe it was, or we didn't have theoretical models of. We had this outpacing deduction thing, which I think is crazy. It looks like calibration is not as necessary for inexploitability as like I thought in advance. We're still actively investigating that. We don't have like hard results that say like you only need a certain amount of calibration. We have results that say you do need a certain amount of calibration. You don't have to hard code belief coherence laws. The thing actually just learns them on its own. You don't have to tell it to satisfy the laws of probability theory. In the course of trying not to lose to the market, it learns probability theory. So you don't need to do that. And I've had a meta update that mirrors general approach of actually trying to turn these big philosophical questions, like how do you make a self-reflective algorithm that understands itself and does math well, is maybe actually doable. Like there's somehow Scott managed to actually put a big dent in this problem, and it makes me want to like try and put more dents in it. So that's a big meta update. I was not expecting this to happen in my lifetime, not in my career anyway. I basically was going to abandon the MIRI like agent foundations agenda because I thought it was hopeless because we weren't going to solve logical uncertainty in the next 30 years. So I was like, AI is going to exist before anyone answers this problem. So like we should probably give up on it. And then Scott didn't care what I said. So thanks to Scott for that work. He's going to be around. He's going to answer questions, hopefully. As you can see, there's already some people in the audience who can also help answer questions, like Sam, Jessica, and Svi. Are these people here? Can Svi, Nate, Jessica stand up? Thanks. Yeah, stand up. Identify yourself. So these guys are co-authors on the paper. They're going to be able to answer questions. And he's not, but he knows stuff anyway. That's Sam. And yeah, thanks to Jimmy. Jimmy's not here, is he? But he helped me with lots of LegTech problems. So that was a big deal. Thank you, everybody. We're on break.